If I gave you a signal that you see on the top frame of this graph, the red one, what would you think is the frequency, content, and the amplitude of the signal that is shown? The extent or the time extent of this whole thing is about 600 microseconds, which is not visible on the bottom, but so you would guess based on total time and the number of divisions, probably around 20 transitions in this whole thing, which would be 30 microseconds or so per transition. So you would expect a signal of around 30 to 40 kilohertz. Okay, that's what you would normally think. But we'll have to guess again because that's nowhere near what this signal actually is, the repetitive part of the signal. It's actually much faster and much smaller than what you're seeing on this graph. So in order to extract the real information in this signal, the real repetitive signal that is hidden in this signal, you would need an amazing instrument called a lock-in amplifier, which will do which has the ability to extract both the phase information and the amplitude information with respect to the known frequency, that is the frequency content of the signal. So if you assume it's 30 kilohertz, then it will tell you what the amplitude of the signal is and the phase of the signal with respect to a reference signal that is also at 30 kilohertz. So I'm not going to give you the answer right now, but we'll go through this presentation, and towards the end of this presentation I'll tell you what the frequency content and what the amplitude is for the signal, and the phase and stuff like that, and by that time you'll have an understanding of what this instrument does. So the contents of this video presentation, it's going to be a fairly long presentation, are as follows. First, the basic theory of operation. Next, we'll talk about the simulation of a lock-in amplifier in LT-Spice. So how do we detect signals better than noise? The importance of filter time constant, which is a critical part of use of a lock-in amplifier. And finally, we'll go through some demos to illustrate some of the points that I've discussed so far. So this is a simplified block diagram of a lock-in amplifier. The lock-in amplifier is this box shown at the bottom, which has two input signals coming in. One is Vn, signal that we're trying to measure, and Vr is a V reference or reference clock. Now the reference clock could be also internally generated within this lock-in amplifier, and what we want to be able to do is to detect the signal, the Vn, which is exactly in synchronous to the reference signal. If the signal Vin and Vr are unrelated, then the output of the lock-in amplifier will be 0. So on the picture above it, we have the block diagram of the signal itself. Vs goes into two parts. On the top, it's multiplied by one component of the reference signal, and then on the bottom side, it's multiplied by a second component of the reference signal. The top one is called the in-phase component, which is basically the clock is at 0 degrees. Which is an arbitrary phase for the clock, and the one below it is 90 degrees shifted away from that particular clock on top. So these are called the in phase and the quadrature phase of the reference clock. Once you multiply Vs by these two phases of the clock, you get two outputs, Vx and Vy, after filtering. So the block in between is the filter, which has a variable time constant, so you can basically adjust how much you want to reject noise and so on. So Vx and Vy are vectors in the two-dimensional plane, and if you look at that as an xy coordinate, Vx is the horizontal component or the cosine component, and Vy is the sine component. For the purposes of analysis, in the beginning we are going to keep the reference clock frequency and the signal frequency different, and we will illustrate what happens when the frequencies are different and when they are the same. We also keep all the phase and amplitudes independent, and that is not there can be any value. And we will change that later on as we want to simplify the equations. The magnitude of the signal is actually shown this on the graph is the R component, which is the square root of Vx squared plus Vy squared, which is the hypotenuse of that rectangle. And the theta is the phase angle between the reference clock and the signal that we're trying to measure, and that is given by tan inverse Vy or Vx. So now we're going to look at one of the signal paths in the lock-in amplifier. That's the in-phase component or the Vx component. How do we get that? So Vs again is the signal that we're talking about, which is V0 times sine of omega s t plus phi s. Vr is the reference clock, which is V1 sine of omega r t plus phi r, the 0 degrees phase clock. So V multiplied is equal to Vs times Vr, which is equal to V0 V1 times sine of omega st plus phi of s times sine of omega rt plus phi of r. That can be written as Vs Vr over 2 cosine of omega s plus omega r t plus phi s plus phi r plus cosine of omega s minus omega r times t plus phi s minus phi r. So this is a trigonometric rule that everybody is familiar with. That is, the product of two sines is equal to cosine of the sum and differences of the frequencies. So where omega s frequency. Now if omega s equal to omega r, which is equal to omega, we can simplify this and write it this as omega s omega r, sorry, Vs Vr over 2 times cosine of 2 omega t plus phi s plus phi r plus cosine of 0 t plus phi 1 minus, sorry, phi s minus phi r. That is because w omega 1 minus omega 2 is equal to 0 because they are equal, omega 1 equal to omega 2. And so we can further simplify this by saying that let the reference clock be of normalized to 1, amplitude of 1 volt. Then we get that V mult equal to Vs over 2 cosine of 2 omega t plus phi s plus phi r plus cosine of omega phi s minus phi r. So V mult is basically the signal at the multiplier output. Now this goes into a low pass filter, and the low pass filter basically cuts off all the high frequency components in the signal. So 2 omega t is going to be twice the frequency of our signal of interest. So it's well outside the bandwidth of the filter. So it's going to be completely cut off, and so we get V mult equal to Vs over 2 times cosine of phi s minus phi r. So this is a DC component. There is no time variable in this. So that means it's a constant value at DC. So this is the second path. The Vs signal split into two. The bottom path is going into another multiplier, and the second multiplier gets a different reference, which is the phase shifted version, 90-degree phase shifted version of the same clock. So that is basically, we're going to add a pi over 4, as you can see in there. So Vr is equal to V1 times sine of omega rt plus phi r plus pi over 4. Now if you go to the math again, you'll basically do almost the same thing until we reach the second last step, where you can see that V mult is equal to Vs over 2 times cosine of 2 omega t plus phi s plus phi r. That is the same as before. Now we get a different second term, the DC term, plus cosine of phi s minus phi r minus pi over 4. So this last term can be rewritten as sine of phi s minus phi r. So instead of a cosine of phi s minus phi r, we have a sine of phi s minus phi r. So the final result that we get after the low pass filtering in the second bottom path is going to be V1 over 2 or Vs over 2. I think I've confused V1 and Vs, or V0 and Vs. So anyway, that doesn't matter. But the amplitude is going to be not very important, but that is Vs over 2 times sine of phi s minus phi r. So this is equation number 2. So coming back to the original picture we had before, we can now say that Vx is equal to Vs over 2, which is the input signal, times cosine of phi s minus phi r, and the bottom signal Vy is it's the same, Vs over 2 times sine of phi s minus phi r, where phi s is the phase of the signal and phi r is the phase of the reference signal, of the 0 phase reference signal. Okay. So we can represent this on the phasor diagram, and we can see that the magnitude as before is square root of Vx squared plus Vy squared, and the theta is tan inverse of Vy minus Vy over Vx, and those two outputs are actually shown on the outputs of the instrument. So you have 2 meters. One is what displays the in phase component, and the second meter shows the quadrature phase component. Also, the lock-in amplifier has the ability to indicate the magnitude R and theta by changing by using an option to switch the outputs to a different format. And there are other formats as well, which some of the advanced lock-in amplifiers can show. So basically, that's how this lock-in amplifier works. We have basically extracted signal Vs out of a noisy environment which contains other signals. But what this lock-in does is basically extract only the signal that is at the same frequency as the reference clock. Now we'll look at the case where the frequencies are different, and what implications it has on the output of the lock-in amplifier. So when we looked at the simplification of the mathematics earlier, we saw that there was a term in the second term which was cosine of omega 1 minus omega 2, or omega s minus omega r times t plus phi s minus phi r. So we can write that as, in this particular case, if they are not equal, they will be omega 1 minus omega 2 times t in general plus phi, which is the difference of phi s minus phi r, which is the phase difference, or the initial phase difference between the two signals. That phase, of course, will change, because if the frequencies are not the same, phase keeps changing all the time. But to generalize this, so this function of cos of omega 1 plus minus omega 2 times t plus phi is a function that is periodic in t. That means we can basically say that this signal will repeat itself every 2 pi of divided by omega 1 minus omega 2 times n, where n is equal to 0, 1, 2. So it's going to be periodic. That means it keeps going to 0 at a certain rate, and the period is determined by this equation 2 pi over omega 1 minus omega 2. Now, if the signal omega 1 and omega 2 are very, very close to each other, then of course this period becomes much larger, whereas if the frequencies are very, very far apart, that's omega 1 and omega 2 are far apart, then this period becomes smaller. So we will look at the implications of these two things next. So if omega 1 minus omega 2 is a large number, that means the frequencies are far apart, then this, if you look at the figure on top, you see there's a frequency domain representation of the signals. Omega 1 minus omega 2 is a line, vertical line, and omega 1 plus omega 2 is the twice the frequency component, or the summation of the two frequencies. So those components will be spread out, will go further out to the right as the differences become larger. So the low pass filter cutoff frequency is shown in dotted line, and if they are omega 1 minus omega 2 is a large number, it's going to fall outside the cutoff frequency. So it will be very easy for the lock-in amplifier to reject this difference frequency. On the other hand, if omega 1 is omega 2 is a small number, that means the frequency of interest that you're trying to measure and the reference signal are very close to each other, then the filter will not be able to reject that signal easily, because it falls within the cutoff frequency of the filter. And so you will see some effects of that. You will see a sinusoidal representation which occurs at a repetitive nature with the period which is given by 2 pi divided by omega 1 minus omega 2. So that is going to be the challenge in rejection of noise, which occurs very close to the frequency of interest, and that's where the importance of selection of the time constant for the filters become very, very critical. So here's the same information that I'm presenting in the time domain. So we have the omega 1 minus omega 2 not being equal. On the top graph, we have the omega 1 almost equal to omega 2. So the frequency of that periodic signal that we talked about earlier is going to be quite large. That means the time is going to it's going to be a low frequency variation in the phase. And as you can see, there are two phase numbers given, phi 0 equal to phi equal to 0 and phi equal to 45 for that initial phase difference. And this phase difference, of course, will manifest itself as a phase in a lock-in amplifier output, and that will vary over time. But this will become very visible if the frequencies are very, very close to each other, that is omega 1 close to omega 2, and it will have a difficult time rejecting this. On the other hand, when the omega 1 and omega 2 are further apart, the frequency of that variation of the phase is going to be much, much quicker, and so the lock-in has a much easier time rejecting that, and because it's outside the low pass filter cutoff frequency. So this particular aspect of the lock-in amplifier might be a little bit difficult to visualize at this point. That is when the two frequencies of interest are very, very close to each other but not completely equal. So in which case you have this time varying component in the phase that shows up on the output of your lock-in. So we look at this in the simulations and perhaps also in the demo to better illustrate this effect. So what we have here is simulation of a lock-in amplifier. It's a simplified version of what a real lock-in would look like. So to go over the major blocks in here, there are two modulator demodulator chips, the AD630, which is used for typically for various operations and demodulation and modulation of RF signals. And this one is being used in a lock-in application the way it's configured. So it's a gain of 1. It requires plus minus 12 volts as provided over here. The inputs are two clocks. One is the clock 0, the in-phase clock, and another clock called the clock 90, which is the quadrature phase clock at the signal frequency of interest that you want to recover. The signal itself is the V-sig over here, which is a 5 millivolt signal, 10 millivolts peak to peak. And the frequency is going to be the same as the frequency of the clock. I've also added an interfering signal here, which will be varied to show the effects of interfering with the main signal, the effects of time constant variations by adjusting the filter that is at the output of the modulator. So there are two filters, one for the cosine in-phase component and one for the sine. The outputs are V filter X and V filter Y. So from these two values, one can calculate the magnitude of the signal, which is going to be the square root of the sum of squares of the V filter X and V filter Y, and the phase angle between the reference clock and the signal is going to be basically the tan inverse of V filter Y over V filter X. So that's shown in these measure statements over here. The phase, for example, T0 is A tan Vy T0 over Vx T0. So that is taken off the average value of the filter X for a certain range. So depending on the filter value, I'm going to change the measurement interval over which I want to calculate the phase to do the averaging better. So for a very short time constant, I'm going to use a shorter measurement window. For a longer time constant, like in case 3, I'm going to use a longer measurement window so that it's fair in terms of settling time and so on. So based on the filter values, I'm going to calculate a tau, which is going to be the product of the resistance times the filter capacitance. And that is used to calculate the window, which is going to be 3 times tau, or about 95% of the settling time for the filter. So I'm going to first run a baseline with no interfering signal. The signal is in phase with the clock 0. So there should be ideally 0 degrees. So the Vx component will be maximum. The V filter X will be maximum, V filter Y will be minimum because you're in phase, and the quadrature component will be close to 0. So let's run this and then document this first. So I just ran the first case where there is no interference. So this is the setup. And I basically took 3 filter settings. The time constants are created by 100 picofarad, 250 picofarad, and 750 picofarad, which corresponds to 10 microseconds, 25 microseconds, and 75 microseconds. So the measurement window would be I would use case 1, I would use this set of measurements, which would be 30 microseconds for the window. Then for case 2, I'm going to use the measure 2 set of measure 2 statements. And for case 3, for the 75, I'm going to use the case 3 set of measurements. And from the log file, I'm going to basically pick out these 3 cases, and then I've written those 3 values down over here. And as you can see, without any noise, the phase for the shortest time constant, I got minus 1.284 degrees. Ideally, it should have been 0. For the 25 microseconds, I got 1.374. And for case 3, minus 1.529. On the left side over here, the graph shows the settling for the 3 cases. The fastest settling is for, of course, the shortest time constant. It's also noisier. The blue one is for the second, and the red one for the final slowest time constant, the longest time constant. If I zoom in here, you'll see the clock and data of the signal are basically in phase. So they are perfectly in phase. As you can see, the amplitude is 10 millivolts for the signal. The clock is plus minus 12 volts. And the zero crossings are right where it should be at 0 degrees. And the slight error that you see in this is probably due to the model that is responsible for the 8630 creating some internal delays or phase errors, which can be, of course, be calibrated out in the real measurement. So next, I'm going to put in a interfering signal at a frequency which is quite far away from the reference from the signal of interest. So what will happen is that the phase will be chopped up by this clock, which is at the signal frequency, and the effect of this out of band noise will actually, hopefully, will not interfere too much, because the amount of energy contained in the in band of the signal is going to be fairly small, and the phase variations will be random around the point where you want to actually do the measurement. So let's look at that case next. So this example shows a 60 kilohertz signal of 5 millivolt amplitude, which is the same as the input signal, at a frequency of much lower value. So it's going to have much less of an effect. And as you can see from the V filter X and V filter Y, the settling at the beginning is the same, but the noise comes in at 475 microseconds in the simulation, and it lasts for about 20 or 30 microseconds. If you look at the X component, or the cosine component, the in-phase component, you'll see that the 60 kilohertz interferes in such a way that it creates points on both sides of the 6 millivolt average level. And for the Y component, the quadrature component is doing the same thing. It's kind of distributed around the 0 value. So if you take the A-tan function of these two, you're going to get a value that is close to the original value. And depending on the averaging effect, you'll see that the value will be different in each of the 3 cases. And the case where you have the longest or the longest time constant, you're going to get the best filtering at the cost of a longer settling time. So, so the green curve shows the shortest time constant, and the red curve the minimum time constant for both these curves. So if you look at the data next, I'll plot that and show you here. So the 60 kilohertz signal does modulate this pretty heavily, and now the results are shown over here for the 5 cycles of interference, and there are 5 of them here over this period of time. And the phase actually for the shortest time constant was minus 1.367 degrees. For the mid case for the 250 picofarad or 25 microseconds, I got 1.352, and the last one minus 1.398. So if you compare with the non-disturbed signal case, the phase didn't actually really move that much. It's fairly close to the almost no effect on the phase error or on the phase measurement of the original signal. So that basically is proven by the point that this signal is highly randomized around the value of 6 millivolts, minus 6 millivolts, and around minus 0. So one would expect that there is no severe error created by the interfering noise. Next, we will go to a case where the signal is right in the band of the signal and it's actually at the same frequency. And here you would expect to see a lot more disturbance because that basically is almost synchronous with the signal, and so it's going to be in band, and so the filter time constants will play a bigger role in how it filters out this disturbance. Now, here's the case where I put in a 500 kilohertz signal for 5 cycles, and it's going to be 180 degrees out of phase and twice the amplitude. So what would happen is that the signal completely reverses during this interval. The V, and I will zoom in and show you in a bit. But you can see the effect of that very clearly here. The green curve is of course the shortest time constant. It experiences the biggest change in phase, and it recovers quickly, but then it also creates the most amount of error during the time the signal is disturbed. The blue one is the intermediate one, and the red one is going to be the slowest time constant, which results in a smaller step change in the phase, but takes much longer to recover. So these windows, of course, are proportional to the time constant. So the shortest time constant will have a window of 30 microseconds. So from 480 to about 510 or so. So it's going to basically see the largest average error and so on. So let's zoom in over here to see what that looks like. As you can see, clearly in the input signal, there's a phase reversal of 180 degrees. So if I put in an amplitude of 10 millivolts and reverse the phase, is going to create a signal that is basically the same amplitude but starting with the opposite phase. So that creates this huge discontinuity, or like an impulse function at this point. And the phase, of course, jumps in all three cases, and the jump is different for different time constants for the filters. And the recovery, as you can see, is also slower and for the slowest time constant. So now if you look at the data that you get after the measurement, for the shortest time constant, the phase becomes measured as minus 7.186 degrees as opposed to being 1.284. For case 2, it's minus 3.862, and for case 3, we have minus 2.283, which is just 0.7 degrees away from the non-disturbed case. So the effect of filtering time constant is very important in lock-in amplifiers, and depending on the kind of noise you expect to see, you should adjust the filter time constant appropriately to get the best accuracy versus the settling time. Now I'm going to try and do another experiment where I put in a very large amount of noise and see what happens if what happens to the signal, actual signal. In this case, in the past three cases, the amount of noise was fairly small and the signal was very much visible in terms of the overall signal amplitude. But now with the extra noise, you should be able to not be able to see the signal of interest, and yet the lock-in should be able to recover that signal, although we don't know what the phase is going to look like, but that's something we can try out next. Now here's the final simulation with very strong amount of noise added. I've got 3 noise sources in series connected to the input, which is still 5 millivolts or 10 millivolts peak to peak. I have a frequency, the first one is at lowest frequency of 57 kilohertz, and the noise starts at 200 microseconds. The amplitude is 50 millivolts or 100 millivolts peak to peak. In addition to that, I have another 100 millivolt peak to peak at 287 kilohertz, and the final one is very close to the actual frequency at 481 kilohertz, 100 millivolts peak to peak. So the total noise is additive, and it's not, of course, going to add linearly because of the phase differences. But you can see that the input signal over here shows is fairly choppy and very noisy. The lowest frequency component shows the best over here, the 57 kilohertz. On top of that, you have the other noise components constructively and destructively adding over time. What the lock-in recovers is the 2 signals below, the V filter X and V filter Y. And you can see the lowest frequency component shows up most strongly, but it's easiest to reject because of the fact that it's way out of the energy of the 500 kilohertz signal. And The amplitude, of course, I want to look at this time because it's going to also be significantly disturbed compared to the previous cases where we saw the amplitude of the lock-in output was not very much changed. It was still around 6 millivolts, which was what we expected from we had in the non-disturbed case. Now, if you look at the data that the measurement showed, for the shortest time constant of 10 microseconds, the phase was measured at 62 degrees, 0.28, 62.28, magnitude of 19 millivolts, which is way off from what it should be of 0 degrees and 6 millivolts. For the case 2, it got better. Time constant was 25 microseconds. The phase was minus 34 degrees, and the magnitude is much closer at around 7.98 millivolts. The best result came with the longest time constant, 75 microsecond, where we had a phase of minus 9 degrees and an amplitude of 6.53. So the phase is off by about 7.8 degrees or so. The amplitude is only off by about half a millivolt, which is excellent considering the amount of noise over here is at least 40 to 50 times larger if they all linearly added up at the point at the worst case. So you can see how amazing this lock-in amplifier can be when it tries to recover a very small signal in the presence of overwhelming noise that is added to it. So here's one final case for the noise type of simulation where I put in a white noise source of fairly high bandwidth, 1 megahertz, and fairly large amplitude. As you can see, the total peak-to-peak swing of the input signal going into the lock-in is almost 1 volt peak-to-peak. Now, from this, you would expect to see, pretty much nothing of use coming out, but actually, this case is actually much easier for the lock-in than the previous case where I had 3 tones, and some of those tones were very close to the signal of interest, and that's why I told you earlier that signals that are more correlated will have a much stronger influence on the phase because they tend to accumulate over that period of time, and the filter has to be have a fairly long time constant to remove it. Now, if you look at the data from this particular simulation, it's quite surprising in some sense. For the 10 microsecond case, the phase came out to be minus 2.072 instead of the minus 1.3 or so degrees we expected. So only about 3.5 degrees of error. Amplitude is very close to the final of 6 millivolts is 5.6 millivolts. For the mid case, 25 microsecond time constant, I got minus 1.607, which is almost on target with amplitude of very close to the real amplitude of 6 millivolts. And the third case, 75 microseconds, I got minus 2.78 and amplitude of 5.95 millivolts. So in fact, in this particular case, case 2 with the medium time constant was actually better. But of course, we know that this has to be averaged over many cycles. And what I did here was to take a measurement in this region over here between 530 or to the end of the simulation, 570 to around 600. I'm sorry, 470 to 600. So that gave us the result in this region. So if you take multiple such windows and average those, you probably will still get a good result for the best result for the longest time constant. So it basically tells you that a very large amount of noise, which is out of band, easily rejected by the lock-in, and white noise is actually not a problem to deal with. So here's a bunch of experiments we're going to try to see the effects of externally induced disturbances on a smooth continuous sine wave signal and see the effects of different frequency components being injected into the signal to see how that affects the magnitude and phase of the lock-in amplifier. So here we have a straight 50 millivolt sine wave input at 0 degrees, 50 kilohertz, and another signal I'm going to try is going to be with some noise injected into it, So this one is got some noise injected at the end of it, as you can see right here, and I'm going to zoom into that a little bit. As you can see, there are two cycles of 10 kilohertz signals injected in at the end, and then it resumes the 50 kilohertz. And another one is going to be a different frequency there. Let's look at that one. And that's the 20 kilohertz injection at the end. And the last one, this is 50 kilohertz, but phase is reversed. So three different types of noise injection, or some disturbances add to the sine wave at 50 kilohertz, and we're going to see how the lock-in responds to these three. So right now we go back to the original signal, the pure sine wave, and we'll zoom in on the oscilloscope and the lock-in. So here is the lock-in. Is reading 7 millivolts RMS on the X, and on the Y it's 0. I've actually set the reference phase to 60 degrees, so basically the Y component is going to be 0 in this case. As you can see, the oscilloscope shows only an X component with the Y component as 0. Now we're going to try out a few things. This is a 1 millisecond time constant. I'm going to increase it to 3, 5, 10, 20. Makes very little difference because the signal itself is fairly clean to begin with, so you won't see much of a change there. Now we're going to add, now we're going to try this first case where we have the low frequency 10 kilohertz interference. So you'll see the lock-in trying to relock to this new signal. And there it's I believe it's locked now, and there's a different phase. As you can see, the amplitude is slightly lower on the X, and the Y is minus 1.5 millivolts. I'm keeping the same reference phase as 60 degrees, 61 degrees. So this is the case where we have this 1 millisecond time constant. If we change that to something higher, let's go back to the main screen here. So at 3 milliseconds it's pretty much gone, and 10 milliseconds it's very, very clean. So the only thing I notice is that the phase itself hasn't changed that much. It's along the diagonal from the center, so the phase is moving in the direction of the vector, which is in the polar coordinates. This would be the phase angle, but the amplitude is actually changing a lot more. So that is a bit surprising to me. So let's try the next signal. Slightly higher frequency disturbance. This is again 1 millisecond time constant. Again, the phase is about at the same position at minus 1.5 degrees, sorry, not degrees, value of minus 1.7 millivolts plus 6 millivolts. So this is about 20 degrees or so, negative 20 degrees. At the same 1 millisecond time constant, now going to 3 milliseconds and 10 milliseconds. So at 10 milliseconds it's almost as good as no disturbance being applied. Again, the interesting thing is that the phase is not changing that much, but it's amplitude that is changing. Now I'm going to go to the highest frequency disturbance. So this is the 50 kilohertz out of phase signal being applied for a short period of time. Again, the phase is moving along this axis. That means it's not changing that much. The phase moving would be in this circular direction, but it's actually moving in the polar direction, which is along the axis of the phase of the same phase angle, whereas the amplitude is changing significantly. So if you look at the lock-in itself, yeah, you can see that the magnitude is changing for both, but this is an XY representation, so it's not easy to see that. But if I go to R theta, you'll see that this angle is not changing that much. It's about 14 degrees, 12 to 14 degrees, whereas this amplitude is switching a lot more, which is what we are seeing in the polar display and the XY display on in the scope. So going back to X and Y. Now I'm going to change the time constant to 3. It's not as well filtered, and at 10 it's better, and at 30 it's as good as the one that we saw at the lower frequency interference. So back to 1 millisecond, pretty large amplitude variation, but the phase variation is there, but it's not as dominant as I expected. So something to think about, I guess. I can show that this is true at any phase angle with respect to the reference by switching the reference 90 degrees away from this point. So this is 90 degrees shift to the left and anti-clockwise shift. So now you can see that the phase is again along this axis, which is almost a constant phase, but the amplitude again is varying around 30%, 40% maybe. If I shift the clock by another 90 degrees, you can see it's moved to this angle. So again, it's fairly constant along this angle, but the amplitude is shifting quite a bit. And one more phase shift, and this is a 270 degree phase shift from the original, so this is right along this axis, but all of them are oriented 90 degrees apart, so that makes sense. And back to the original. So this is with the 1 millisecond time constant. The interference signal has got multiple components of different frequencies, and it's going to be very large. So this is about 100 millivolts peak to peak, and my signal that I'm trying to measure is still the 550 kilohertz signal at this time at 5 millivolts instead of 50 millivolts. So this is about 20 times larger. Of course, the lock-in can do much better than this, but this is just for demo purposes. And I have multiple components in here, and I can show you those components in this one. We have 3 components. The first one is 17 kilohertz at 100 millivolts. The second one is 23.5 kilohertz at same 100 millivolts, and the third is 49 kilohertz at 100 millivolts. So this one is going to interfere the most, the 49 kilohertz, because it's very close to the 50. But when they all add up together, they result in about a 200 millivolts peak to peak signal. 100 millivolts still peak to peak, because they constructively and destructively interfere at various points. So we go back to the scope to see what we got here. First I will show the clean signal as before. and then we will add this interfering signal. So right now the interfering signal is off, and so we have a very clean phase. Just if you look at the lock-in, the amplitude is 0.7 RMS, and the phase, the X is 0.7 RMS, which is also the amplitude, because the Y component is almost 0. And I put in a phase of reference phase of minus 63 degrees to bring the output to 0 on the Y axis. So you can see it's around 0.7 to 0.8 on the X axis, but 0 on the Y axis. So now this is of course clean with the maximum filter time constant. I'm going to bring it to 1 millisecond, and you can see with the 5 millivolt there is quite a bit of noise because of this is actually a mixer, which since I'm using a external mixer to add these two voltages, there is some other kinds of external noise that is also feeding into this, which is causing the lock-in to have a much larger spread in terms of the noise. So now I'm going to add the other signal, the channel 2 signal, with the extra noise in it, and you can see basically almost no change, and that's because of the fact that this is extremely white, or much more white than the previous signal that we had, and the lock-in has no problem rejecting wideband white kind of noise interfering with it. So looking at the output on this one, again you can see it's pretty much very difficult to see, of course, the dynamic variations, but on the scope you can see this is with the noise, and then and this is without the noise. It's not a huge amount of difference in terms of the response of the lock-in. Most of this noise is actually external and not the added signal that I just put in. Now I'm going to turn on the higher order filter, longer time constant filter at 30 milliseconds, and this is without the noise. It's now pretty much clean, and now with the noise added, channel 2 noise that is, while the amplitude changed a little bit, it's very, very quiet as before. So the filter time constant is very important. Changing it back to 1 millisecond, 3 milliseconds, 10 milliseconds, and 30 milliseconds.